Hello everyone, I am Pierre Pradic and I will be discussing our joint paper with Tito and Camille. So the paper in question introduces a possibly new notion of transduction and a corresponding class of string-to-string function that we call comparison-free polyregular. So before introducing this class proper and our results, I will first discuss two notions of string-to-string transducers. The first one being the transduction that are defined by two-way automata. So to cut things short, a two-way automata is basically like a finite state automaton, except that we have a reading head that can go either left or right at each transition. And in addition to just having an automaton structure, we also have an output which is being produced at each step. So here you have an example of a function corresponding two-way automata where the states are labeled by the direction in which the reading heads should go. And right now I'm going to execute a run of this automaton over the input word ABC sharp BAC sharp CA, which is pictured below. So first we go into this initial state. We move right until we find some sharp, then we go back, and then we come back to the sharp, and we come back to the initial state once we've made that crossing and went through all these three states. So it should be fairly clear by now that indeed this device does implement the function that is pictured below, which takes every subword between sharps and output the word followed by its reverse before moving on. So these two-way transduction, the transducers, they define a class of string-to-string function which are called the regular function. This class of function is relatively weak from a computational standpoint, but they are very well behaved from the point of view of automata theory. So if we only consider those transducers that actually always terminates, it's fairly clear that those functions have a linear growth rate. Something which is much less clear is that they are actually closed under composition. It's not something that is super obvious if you just take the 2TFT characterization of them. And something more obvious is that from the point of view of automata theory, they also preserve regular languages by inverse image, which is sort of nice. So another thing that witnesses that this class is rather nice and robust is that there are some other natural characterization of it. So one via a notion of logical interpretation using MSO. There's also a one-way transducer model for this. And there are also various formalisms based on functional programming languages or basic combinators for this. A recent work of ours also give a characterization using linear lambda calculus and Church encodings. So the topic of this talk is a subclass of polyregular function. So polyregular functions are a larger class of string-to-string transduction, which has been given a lot of attention recently. So essentially, these functions enjoy a lot of the same property as regular function, except that they also have they are not restricted only to functions of linear growth. They can have a polynomial growth. If you only restrict to functions of linear growth, you get back exactly regular functions. So another thing that insists that this class is sort of robust is that it has also a lot of alternative characterization which are somehow natural. So for instance, there's this very nice result which says that it's the same as having a sort of MSO interpretation. And there's also a nice characterization using basic combinators. So for the purpose of this talk, we're going to mostly focus on this last characterization, which is in terms of so-called pebble transducers. So what's a pebble transducer? So formally speaking, you can regard pebble transducers as a generalization of 2D FTs. Instead of having a single two-way reading head, this time around we have a stack of reading head. So here we speak of K pebble transducers. This K is supposed to give a bound on the number of reading head that you can have. So what can you do in this sort of thing? You can move your head left and right. And since you have a stack, you can also push and pop heads in this stack. And something else that you can do is to decide whether or not you're going to this state or this other state. You can or to decide whether you output something or something else. You can actually compare the relative position of two heads. So here I'm giving the example of the paradigmatic function, polyregular function, which is this sort of squaring within the lining, which essentially takes this input and duplicate it as many times as you have letter in the input, and at each step it underlines sort of the current letter. So here we have a picture of a pebble transducer. Let's see how it works in action. So first you have this main reading head which is pushed, and then you have a secondary reading head which is pushed and traverses the whole word, outputting a copy of the word. But note that when it actually moves on top of the main reading head, it actually underlines the letter the main reading head is pointing to. Okay, and once we went through the word with the main reading head, we just pop the main reading head, which means that we terminate the computation. Okay, so here you have a lot of power because you have multiple reading heads, but also you have the ability, here we crucially use the ability to be able to compare the position of the two reading heads. So essentially the one way you can approach our paper is that you can ask, okay, but what happens if we don't allow to compare the two positions in the reading head? You're still allowed to push, pop, and move as you wish, but you don't allow to compare. If you do this, well, squaring within the lining becomes impossible, but you still have non-trivial function which have quadratic growth, such as this comparison-free squaring, which is going to be the sort of paradigmatic example of a comparison-free polyregular function. So here I'm also giving you a machine which implements this, and you can see that it's very similar to what's going on with the squaring within the lining, with the difference being that there is no need for this comparison in the transition. Okay, so we can make this definition just fine, but okay, so what have we got to say about this? So our main contribution is a study of this class, which means that in practice we give alternative characterization of this, which are not necessarily based just on this pebble transducer model. And we also formally prove that this thing is indeed separated from a from general polyregular function. This means in particular that we prove that squaring with underlining is actually not feasible in this model. And along the way, while we did this study, we also needed to establish some nice property of this class of function, such as closure by composition, which is still non-trivial, and also a pebble minimization result, which I'm going to detail later. Okay, so first I'm going to begin by summarizing the two main alternative characterizations that we have of this class. The simpler one is a presentation in terms of a certain operator that we called compositions by substitutions. Formally speaking, given a function f, with the codomain I star for some finite index I, and a family of functions indexed by this same I. As long as all the GIs there have the same domain as F, we can define the value of CBS of F and the GIs as applied to some input word W by first evaluating F over W, and then in the resulting word substitute each letter I by GI of W. So if you take this operator and you throw in all regular functions, for instance, you can get nonlinear behaviors. So for instance, this comparison-free squaring you can implement using CBS and regular function here f, gx, and ga. So here we have just the identity and constant functions, which are easy enough, and here f, which is not fully specified, but which can be done using a regular function because it's just inserting a letter after each a. So it's actually just a normal morphism. So both comparison-free polyregular function and polyregular functions are closed under this operator CBS. And you can use this to give an alternative definition of comparison-free polyregular functions, which is just take the smallest class, which has regular function, and close this under this operator CBS. So this is not so hard to prove because you can just go by induction on the number of pebbles of a pebble transducer to translate it into an expression with just CBSs. And conversely, if you have an expression with CBSs, you can run an induction on the nesting of this CBS operator. And if this nesting is K, you can get back a K pebble transducer. The main appeal of this characterization is that it's actually more convenient to manipulate a function given as composition by substitutions rather than just a pebble transducer. So for the other main characterization that we have well, the road that led us there was a bit indirect. The reason we actually started to study this class of function was actually motivated by our previous work on linear lambda calculus and church encodings. And in fact, by doing a small variation of the previous result I mentioned about regular function, you get back a class which corresponds exactly to this comparison-free polyregular functions. And there's a non-trivial correspondence between lambda calculus and comparison-free functions. So for the sake of making the paper self-contained, this is not presented in this paper. However, just doing this, it hinted at the following theorem that states that comparison-free polyregular functions are closed under composition. This is completely trivial if you take a lambda calculus based characterization, but this is not so trivial if you just look at pebble transducers, much like it is non-trivial that two-way transducers are closed under composition. So in this paper, we have proven this theorem just using automata theoretic tools. So with this in hand, we can actually give an alternative characterization of comparison-free polyregular function, which is just based on giving basic functions and closing the class under composition. So here we can say, well, if you throw in all regular functions plus this comparison-free squaring that I mentioned earlier, you get back all comparison-free polyregular functions. This is very much analogous to what's going on with the polyregular function. Like if you throw in squaring with underlining, you get all polyregular function instead of comparison-free. One reason why these sorts of decompositions are appealing is that you can, like here I just gave all regular functions plus one combinator, but you can also decompose regular functions into more basic combinators. And so that's sort of nice. Okay, so this is pretty much what I had to say for the alternative characterizations of this class. Now I'd like to move on to the separation results. So here you can see our two main separation results. So for the first one on the left, if we identify words over the unary alphabet A with numbers and words over the alphabet A and sharp as a list of numbers, the first theorem essentially tells us that we cannot have the sequence of sequences of the first n number represented by a comparison-free polyregular function. This function, it's something that is easily seen to be polyregular. And in fact, because comparison-free polyregular functions are closed in the composition, as a corollary, you can deduce from that that squaring with underlining is actually not a comparison-free polyregular function. This result can also be used to show that comparison-free polyregular functions are incomparable with another class of transactions called HDT0L transactions, which I won't detail further here. Here, the second theorem tells us that this function, which is sort of a map of a squaring function over these words a's seen as integers, is polyregular, but not comparison-free polyregular function. So what this entails in particular is that the class of comparison-free polyregular function is not closed under a certain map operator. So this is sort of interesting because this tells us that there seems to be an obstruction to giving a characterization of comparison-free polyregular function using list processing functional programs, much like Boyancic and co-author did for polyregular functions. So now let's try to look at some details on how these two theorems are proved, starting with the second one. So this starts off by proof by contradiction. And the way we prove this, we sort of say, well, let's assume that G is comparison-free polyregular. Well, let's argue that further we could assume that if it were the case, G is actually computed by some 2-pebble transducer. We can actually make that assumption because comparison-free polyregular function satisfy this pebble minimization characterization, which is that if you have a comparison-free polyregular function with a growth at most n to the k, then you can implement it using a k-pebble transducer. So there is an analogous result for pebble transducers and the general polyregular function that we just adapted to our setting. So unfortunately, we did not find a sort of a black box approach to this, so we had to readapt the whole proof, but the same ideas could be reused here. So once you have this in hand, you can make that assumption that, well, if G was actually implemented by some comparison-free polyregular function, then you can implement it using a 2-pebble function, and it's got this very specific shape where all functions inside are regular except of this CBS operator, and you can conclude with a sort of pumping argument and using the pigeonhole principle, knowing that every function inside has linear and asymptotic growth. There might be a simpler way of doing this, but we found it convenient to go through that general result, and like that general result of pebble minimization is also of independent interest. So for the first result, we sort of observed that the function that we have here is sort of non-uniform. So the way we formalize this is by remarking that it has unboundedly many maximal A factors, and comparison-free polyregular function with unary input cannot have unboundedly many such factors. So to show this, we actually give a more precise characterization of a polyregular function whose input alphabet have a hard unary. So actually those maximal factors, you can find them among polynomials. And to find those polynomials, you can use this characterization of the function. So for using this notion of polypumping sequence. So these polympoping sequences are essentially the comparison-free polyregular function with unary input alphabet and a trivial state space. If you close this notion under ultimately periodic combination of functions, you get back all comparison-free polyregular functions with the unary input alphabets. So using this characterization, you can show the lemma using an induction of this, and the characterization itself is rather straightforward to prove by induction on a number of pebbles or CBS operators that you can find in definition. Okay, so now that I've went over some of the main results in the paper, let me discuss very briefly some further topics. So one further topic which is of interest is the first order fragment. So first order fragments exist for regular and polyregular functions. For comparison-free polyregular functions, you can come up with a natural notion. So here, for instance, here's some official definition for what should a first order comparison-free polyregular function is. Here, this is the CBS-based definition, where you replace regular by FO regular everywhere. Once you have this characterization, you can ask the question of other characterizations, and there is one which is very interesting, which is in terms of interpretations. So I'm not going to go over the details, but essentially this is about one-dimensional interpretation. And the main difference with the general polyregular case is that when you take a product of structure, you're not allowed to compare what's going on in a tuple. You're not allowed to compare between coordinates inside the same tuple. You only compare coordinate-wise. So arguably, this would settle the question of what is the logical characterization of comparison-free polyregular function using a decomposition that isolates the non-first order behavior. And once this would be done, it's believable that it would be enough to actually settle, the question of the more important characterizations of first order comparison-free polyregular. Of course, there are other topics you can think about. So here's a non-exhaustive list. So first, there's also the natural question of, okay, can this sort of approach be extended to tree transduction? And in fact, there is a sort of very natural generalization to trees of a comparison-free polyregular function. Some of the problems we haven't touched are like decision problems for this. Like, can we decide, for instance, equivalence of comparison-free polyregular functions, or separation problems? So there is this paper by Duano-Tabo, which is very recent, which actually gives a sort of decision procedure to decide whether something is comparison-free polyregular or not, assuming the input is polyregular and of quadratic growth. And something that pertains more to our interest, Tito and I, is to look for characterization of the FO case in terms of linear lambda calculus. This is something we're going to work on pretty soon. Okay, so now I will wrap up. So here you can see summarized the main result I've presented. I've highlighted in red like the two main technical ingredients in the paper, like at least the main the harder theorem from a technical point of view, which is closure under composition and pebble minimization. With that said, thank you for watching, and we'll be happy to take questions either at the conference or via email even. Bye.